Welcome back to the Deep Dive. Today we are taking on, well, a truly monumental task. A deep dive into the insights, the history, and the profound humility offered by Carl Sagan's seminal work, Pale Blue Dot.
It's so much more than a book about space, isn't it?
Oh, absolutely. It's really a mandate for human survival, one that's rooted deep in our past and aims squarely at a multi-world future.
Our mission today is really to pull out the core arguments. Why does humanity need to expand into space? How did science systematically dismantle our cosmic arrogance?
And maybe most surprisingly, what have our dead planetary neighbors taught us about protecting the only home we actually have?
That's the key.
And we have to begin exactly where the book does, with that image, that single lonely photograph of Earth taken by Voyager 1.
As it turned back from the immense darkness of the outer solar system.
I think most people see the photo and just don't realize the sheer engineering challenge of even getting it.
It was not trivial at all. Securing that image was a huge logistical and engineering gamble. Voyager 1 was already way past Saturn.
Right.
And to turn the camera back toward us, toward the inner solar system, meant aiming it dangerously close to the sun.
You risk burning out the camera.
Exactly. There was genuine concern within the Voyager project about, frying the highly sensitive Vidicon camera system, a system they might still need later.
But the philosophical payoff, it was worth the risk. When you look at that photograph taken from 6 billion kilometers away, what does it actually show you?
It just delivers this visceral sense of our true scale. From that distance, Earth is just an inconsequential, solitary point of light.
We'd seen photos from the moon before, the Apollo shots.
Right, and those already showed our smallness. But the pale blue dot image pushes that realization 100,000 times farther away. It's less than a single pixel.
And it's the absence of detail that's so powerful. You search for any sign of it, cities, borders, anything.
And there's nothing. The source material says it plainly. No sign of humans in this picture, not our reworking of the Earth's surface, not our machines, not ourselves.
It's the ultimate antidote to human self-importance.
It really is. Think of the endless violent history of human conflict, all driven by territory and nationalism, our obsession with statecraft, with borders.
All of our collective energy?
It's nowhere. It just underscores, as the sources put it, the folly of human conceits. On the scale of worlds, let alone stars or galaxies, we are, without question, just a thin film of life on an obscure and solitary lump of rock and metal.
I think a lot of people who see the image are drawn to that ray of light, the one that seems to frame the Earth. It's so easy to see that as, something special, a halo.
And that's exactly the kind of ego-driven interpretation the book just swiftly corrects, that special sunbeam. It's simply an accident of geometry and optics.
Look at the light.
Nothing more. The sun emits its radiation evenly in all directions. If the spacecraft had snapped the picture a few degrees to the side, or even just half an hour later, that ray of light would have missed Earth completely.
Let's talk about the color itself. The pale blue that gives it the name. What creates that?
It's two main things. First, the oceans. They cover about 70% of the planet, and water absorbs red light a little better than blue light, so the light that scatters back to space is skewed blue.
And the second?
The atmosphere. It scatters blue light much more efficiently than red light. It's the same reason our sky looks blue when you're standing on the surface.
And the little white patches we can make out.
Clouds, of course.
Huh.
On any given day, Earth is about half covered with whitewater clouds, which are super reflective.
So the key thing is that these elements, water, light scattering, clouds, they're not necessarily unique signs of life.
Not at all. They're features shared in some form by lots of bodies in the solar system. The color screams physics and liquid water, not necessarily life.
So, if the image strips away all our conceits, if it reveals our true circumstance, what's the non-negotiable conclusion we're supposed to draw from that?
It's a powerful ethical statement born right from the science. The sources are unequivocal. They say the image underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
So it's a demand, really,
Yeah.
to stop prioritizing our tiny local squabbles.
Exactly. To stop focusing on our artificial divisions when you're faced with the immense backdrop of cosmic reality. It's a call for global solidarity in the face of our planetary isolation.
That humbling realization leads us perfectly into the core argument for expansion. It's not just about curiosity, is it? It's about survival.
That's right. Which brings us to part one, the nomadic imperative.
This idea that exploring isn't a choice, but an evolutionary necessity, literally built into our DNA.
And the argument is rooted deep, deep in our history. For a staggering period, 99.9% of the roughly 4 million years since our lineage split from other apes, we weren't settled.
We weren't farmers or city dwellers.
No, we were hunters and foragers, constantly wandering the savannas. Our survival depended completely on two things: cooperation within our little group and technology, which back then just meant tools and fire.
So the sedentary life, the one we all live now, is just this tiny blip on the evolutionary timeline, only the last 10,000 years.
And the book suggests this really rapid transition has left a mark on us. Even with all the stability and food that agriculture brought, this settled life has left us feeling edgy, unfulfilled. There's this persistent restlessness in human culture, a craving for the horizon.
So why would natural selection favor that? Why is the appeal of far-off places a trait that was, quote, meticulously crafted by natural selection?
Because the world is fundamentally unpredictable. I mean, just because you have good harvest for 10 years doesn't mean the 11th won't bring a devastating drought or a volcanic winter or some, strange chill that lingers in the summer.
If you're all in one place, you're vulnerable.
Totally. If your whole population is in one valley, a regional catastrophe, a single crop disease wipes you out. Our survival as a species probably owes a lot to a restless few, the ones who are always drawn to discover new lands and scatter our genes across the globe.
It's the ultimate evolutionary insurance policy.
Exactly.
And this isn't just a modern impulse for space travel or something from the Renaissance. We see this play out on a massive scale throughout history.
Oh, absolutely. I mean, think about the first great migration into the Americas, maybe 11,500 years ago. The oceans were lower. People just walked across the Bering Strait from Siberia to Alaska.
And from there,
Within 1,000 years, which is a phenomenal pace for pre-industrial people, they had reached Tierra del Fuego, the very southern tip of South America. That shows a deep, continuous impulse to just keep pushing.
and it wasn't just a European thing either. The book makes it really clear that exploration is a universal human trait.
For sure. Think of the Indonesian Argonauts who mastered the sea and explored the Western Pacific, even settling Madagascar thousands of miles from home. Or the Ming Dynasty Chinese fleets in the early 15th century.
Those were massive undertakings.
Huge! They crisscrossed the Indian Ocean, set up naval bases in Zanzibar, rounded the Cape of Good Hope, and sailed into the Atlantic long before any Europeans did.
There's a powerful irony there, isn't there? That when Europeans started their age of discovery, they were often discovering continents, the Americas, Australia, that had been settled by Asians thousands of years before.
It just underscores the universality of the drive. But the thing is, the nomadic imperative hasn't gone away. Today, people are still moving, driven by the need to flee famine, war, oppression.
And it's probably only going to get more intense with climate change, creating huge new populations of environmental refugees.
Right, but the conditions have fundamentally changed.
How so?
The lands we run to now are already settled. There is no open frontier left on Earth. When people arrive in a new country today, they often meet others who are, unsympathetic to our plight. The resources are diminishing. The old safety valve is gone.
And this lack of a frontier leads to this incredibly personal story in the book, the anecdote about the author's own family.
Yes, the story of Leib Gruber, Sagan's grandfather. It just encapsulates that desperate, hopeful drive. He grew up in Central Europe, in what was the Austro-Hungarian Empire.
He was incredibly poor.
So poor that the only honest work he could find was ferrying people across a river on his back. He was hired out, as the source says, like four-footed animals. So in 1904, he makes the agonizing decision to flee to the New World, leaving his wife, Chaya, behind.
That decision to leave everything is the ultimate expression of that imperative, just driven by pure desperation.
And his wife, Chaya, her vulnerability when she finally joined him is it's heartbreakingly summarized in the ship's manifest. She was traveling in the cheapest class on a ship called the Batavia.
And the manifest noted.
She couldn't read or write, couldn't speak English. And when they asked her, as required by immigration, how much money she had to start her new life, she replied with a single word that defines both her vulnerability and her hope: $1.
$1. That single detail just captures the immense risk, the desperate hope, and the deep human need to find a better place. A need that now has to look outward, beyond Earth, because there are no new continents left.
And that imperative is what fuels the need for exploration.
If that imperative provides the engine, then part two provides the necessary humility. This is the history of how science systematically tore down human self-importance, the great demotions.
It all started with this deep-seated delusion that the Earth was right in the middle of the heavens.
And this wasn't some fringe belief.
Oh no, for 3,000 years this was just conventional wisdom, a massive transcultural truth embraced by, well, by nearly every major thinker. Aristotle, Plato, St. Augustine, St. Thomas Aquinas. The cosmos was imagined as this perfect, crystalline, cosmic clockwork built for one purpose.
Which naturally leads to an incredible level of human conceit.
Of course. If the world is a perfect machine built for us, then the logical conclusion is that the world's perfection would be incomplete without us.
The poet John Donne wrote that man is not a piece of the world, but the world itself.
Right. The source material jokes that an uncharitable alien observer might have concluded, this must be the planet of the idiots, for holding a view like that.
But then, in the mid-16th century, you get the Copernican challenge, which starts that whole dismantling process.
Copernicus proposed the sun-centered system, but at first the establishment only tolerated it as a computational convenience.
So just a mathematical trick.
Exactly. It made the math easier for predicting where planets would be, but they told everyone it wasn't a serious challenge to theology. And the main physical objection was the lack of observable annual parallax.
Can you break that down for us? What exactly is parallax?
Sure. Parallax is just the apparent shift in an object's position when you change your viewing angle. If you hold your finger up and look at it first with your left eye, then you're right, your finger seems to jump against the background. That's parallax.
So if the Earth is moving.
If the Earth is truly orbiting the sun, then every 6 months, when we're on the opposite side of our orbit, we should see nearby stars shift a tiny bit against the backdrop of distant stars. Geocentrists said, well, we can't see that shift, so the Earth must be stationary.
And the Copernicans' response to that?
Their only counter was that the stars must be unimaginably farther away than anyone had ever conceived. So far that even the huge shift in Earth's position wasn't enough to produce a detectable shift in the stars' positions.
Which to the geocentrists must have sounded ridiculous.
They called it ludicrous, a desperate attempt to save a flawed idea.
And all of this culminates in the fate of Galileo, who just keeps teaching that the Earth moves, creating that brutal clash between observation and dogma.
Galileo's condemnation is, well, it's one of the greatest lessons in scientific history. He was threatened with torture, sentenced to house arrest for life. He was forced to publicly recant, to curse and detest the same errors and heresies.
And it took the church a very long time to come around.
Almost 2 centuries. Until 1832 for the Roman Catholic Church to finally take Galileo's work off the list of forbidden books. It's a powerful reminder that deeply held opinions don't surrender easily to inconvenient facts.
But the facts kept piling up. What were the astronomical discoveries that finally gave irrefutable proof?
There were 2 big ones. The first was James Bradley's accidental discovery of the aberration of light in 1725.
Okay, aberration of light. What did he actually see?
He was trying to measure parallax, but he couldn't. Instead, he noticed that all the stars seemed to trace little ellipses in the sky over the course of a year. He realized it was like being in a speeding car during a rainstorm. If you're standing still, rain falls straight down, but if you're moving forward in a car, the rain appears to be slanted toward you. Because the Earth is moving through space, starlight appears to come in from a slightly slanted direction.
And if the Earth were stationary?
This universal annual shift in the apparent direction of light just wouldn't happen. It was a physical effect that depended directly on the Earth's velocity.
That is profound. And then the final nail in the coffin was actually seeing the parallax.
Yes, the definitive direct observation of annual parallax finally came in 1837. After centuries of trying, better telescopes and techniques let astronomers measure that tiny predicted shift that pounded the final nail into the coffin of geocentrism.
The first great demotion was complete. But they didn't stop there, did they?
Not even close. The next blow was the plurality of worlds. Once Galileo pointed his telescope at the moon and the planets, he saw mountains, craters, atmospheres. These weren't perfect spheres, they were other worlds.
Like our own.
Exactly. It was a massive downlifting experience for human pride. It suggested the Earth might be common.
And then we realized our sun wasn't special either. This is galactic insignificant.
Correct. By the 19th century, it was clear the sun is just one lonely star in the vast Milky Way galaxy. And we're not even in a good neighborhood. We're in an undistinguished sector of an obscure spiral arm, about 30,000 light years from the center.
From the center of the universe to the cosmic suburbs?
Yes, precisely. And then the scale just exploded with cosmic scale. The Milky Way wasn't unique either.
It's one of hundreds of billions.
Right. Modern deep space photos often show more galaxies beyond the Milky Way than stars within it. And because the universe is expanding, observers on any galaxy would see all the others running away from them. There's no privileged spot in space.
Then there's temporal insignificance. We're just late to the party.
Very late. If you compress the history of the universe into one day, our species only shows up in the last fraction of a second. The book notes that 99.998% of cosmic history was over before we even got here.
So we couldn't have been part of the plan from the beginning.
We weren't there. Then you get Einstein and Darwin. Einstein removed our privileged frame of reference in physics. And Darwin delivered the ultimate biological demotion, showing we're connected to all other life through natural processes. We weren't specially created.
And yet, even with all this deprovincialization, humanity has tried a modern philosophical comeback, the anthropic principle.
This is the ongoing attempt to find some unmerited privileged position. There's the weak anthropic principle, which is fine. It just says we observe a universe compatible with our existence because if it weren't, we wouldn't be here. It's a tautology.
But the strong anthropic principle is the one that really tries to put us back in the center.
Yes. The strong principle suggests the universe was deliberately set up so that humans would eventually come to be. It argues the physical constants, gravity, speed of light, all of it, are so finely tuned that it must have been designed for us.
I love the book's counter-argument to this.
Yeah.
It's so simple and elegant.
It's brilliant. It points out that the same laws and constants you need to create our kind of life are essentially the same laws and constants required to make a rock.
So a rock could make the same argument.
If stones could philosophize, they'd be arguing for a strong lithic principle, claiming the universe was finely tuned for them. The anthropic principle is just the latest, most sophisticated version of human exceptionalism.
And the final, ultimate demotion is the concept of the multiverse.
Andre Linda's cosmology. It suggests our entire observable universe is just one bubble in a vast, perhaps infinite foam of universes, a larger cosmos. Our universe in this view is just a newly formed backwater.
So even our pride in living in the only universe is denied to us. The conclusion after all these demotions seems pretty clear.
We found wonders our ancestors never dreamed of, but so far, beyond Earth, other worlds are desolate and barren. We have every reason for humility.
If the great demotions taught us cosmic humility, Part 3 shows us that this exploration isn't just humbling, it's actively life-saving. We're moving into comparative planetology.
Right, where studying dead worlds teaches us how a planet can go wrong.
It's the critical link. By looking at the extremes, Venus as a runaway greenhouse, Mars as a deep freeze, we get the perspective we need to understand the delicate balance here on Earth.
It gives us validated worst-case scenarios.
Let's talk about that fascinating thought experiment that actually happened. The Galileo Earth flyby in 1990. The probe used Earth for a gravity assist and tested its own instruments to see if it could detect life here.
The results were so cool. The instruments looked for what scientists call disequilibrium in our atmosphere, a state that shouldn't exist without something active, like life, constantly messing with it.
And the big signature they found.
The simultaneous presence of vast amounts of oxygen and small but measurable amounts of methane.
And why is that combination so weird?
Chemically, oxygen is incredibly reactive. In an oxygen-rich atmosphere, methane is super unstable. It should rapidly break down into water and CO2, leaving almost no trace.
But we have it.
We have about 1 part per million, which is an immense discrepancy. The only possible explanation is that something is pumping methane into the atmosphere so fast that the chemical reactions can't keep up.
And that something is life.
That something is life. Bacteria in bogs, rice cultivation, and yes, the sources specifically mention bovine flatulence from our massive herds of cattle. Methane in an oxygen atmosphere is the clearest sign of life on Earth.
Okay, that's the biological signature. What about the signature of intelligence? What did the high-res images show?
At a resolution of about 100 meters, the planet is just covered with geometric structures. Straight lines, squares, rectangles. The observer would conclude the dominant life forms have a simultaneous passion for territoriality and Euclidean geometry.
They see our farms and our property lines.
Exactly. And when the resolution gets down to the meter level and you see what's moving, who do you conclude are the dominant organisms?
Not us.
No. They see the roadways filled with streamlined, multicolored beings a few meters in length, politely running one behind the other. Our cars. The logical conclusion is that the whole road network is built for these dominant beings.
Then we're just tiny parasites that ride inside them occasionally.
That's the perspective. But the environmental conclusion the alien observer draws is even more damning.
What do they see?
They see smokestacks pouring CO2 and chemicals into the air. They see the cars doing the same. They spectroscopically find high levels of CFCs, which are both greenhouse gases and ozone destroyers. The environment is being destroyed by massive, uncontrolled experiments.
And the ultimate question this observer is left with.
They look at all the evidence, the environmental destruction, the ozone depletion, the accelerating warming, and they wonder, haven't they noticed what's happening? Are they oblivious? Are they unable to work together?
Perhaps, they think.
It's time to reassess the conjecture that there's intelligent life on Earth. The environmental collapse we see is the most powerful argument against our own intelligence.
Let's pivot to how space research has actually helped us mitigate some of these catastrophes. First up, ozone depletion.
The danger from CFCs, the chemicals destroying the ozone layer, was recognized using chemical data derived directly from planetary studies. The researchers, Roland and Molina, relied on data about chemical reactions involving chlorine that had been measured, in part, with NASA funding for studying other planets.
And the specific planet that helped.
Venus. Its atmosphere has a lot of chlorine and fluorine molecules. Scientists trying to understand the weird chemistry high in Venus's atmosphere provided the key data that showed just how dangerous those same chemicals were to our own ozone layer here on Earth.
Okay, second connection. Global warming and validating our climate models.
Right. We can't really trust a climate model unless it's been tested. We don't have a second Earth to experiment on, so our models have to successfully predict the climates on other worlds.
If it fails on Venus or Mars.
We have every reason to mistrust its predictions for Earth. The fact that our best models work very well in predicting the runaway greenhouse on Venus and the deep freeze on Mars gives us critical confidence in them.
And modern climate modeling has its roots in studying Venus.
It does. James Hansen, one of the key figures, focused his entire doctoral thesis back in 1967 on the atmosphere of Venus. He was trying to figure out why its surface is 860 degrees Fahrenheit. The conclusion, a runaway greenhouse effect from CO2, was the intellectual springboard that led him to think about the escalating greenhouse effect on Earth.
The final and maybe most surprising connection is the concept of nuclear winter.
This came directly from studying Mars after the 1971 global dust storm, which was watched in detail by the Mariner 9 spacecraft.
How did a Martian dust storm lead to a theory about nuclear war?
During that dust storm, Mariner 9 saw a massive temperature inversion. The high atmosphere got much warmer because the dust was absorbing sunlight, but the surface got much colder because the light couldn't get through.
So scientists just applied that logic to Earth.
The TTAPS team did. They calculated what would happen if you injected huge amounts of dust and soot into Earth's atmosphere, like from thousands of nuclear firestorms. You'd get global cooling, darkness, freezing temperatures. The entire nuclear winter hypothesis came from Martian data.
Incredible. Now let's turn to part 4, the robotic frontier, the amazing achievements of the Voyager missions.
The Voyager's really built on a legacy. The U.S. had already had some big firsts, the Van Allen belts, Mariner 2 to Venus, but Voyager was on another level of ambition.
And Voyager 2 in particular was an engineering masterpiece, using that celestial billiards principle, gravity assist.
Right. It used Jupiter's immense gravity to pick up a speed boost of nearly 40,000 miles per hour, which flung it toward Saturn, and then Saturn flung it to Uranus, and so on. It had to do that because its own engine couldn't get it to the outer planets in a reasonable time.
And the planetary alignment needed for that to work is a once-in-a-lifetime, or rather once every few lifetimes event.
Exactly. The sources note the last time those 4 planets lined up like that was during the presidency of Thomas Jefferson. It was an opportunity that could not be missed.
When Voyager 2 finally reached Neptune, the signal it sent back was almost impossibly faint.
The received signal power was only 10 to the minus 16 watts. The analogy they use is like comparing the diameter of a single atom to the distance from the Earth to the moon. That's the ratio. It's like hearing an amoeba's footstep across billions of miles.
And the genius was keeping it alive for so long, thanks to human problem solving back at JPL. Let's talk about the first crisis, the receiver failure.
This was a human error and a failed component. A command was accidentally missed, which caused Voyager 2 to switch to its backup radio receiver. Problem was that backup had a faulty capacitor.
A single capacitor.
A single tiny capacitor that was essential for the receiver to lock on to the radio signal from Earth. Without it, the spacecraft was effectively deaf.
Out of contact for a full week. How did they solve that?
Pure, meticulous knowledge of the spacecraft. They realized that even though the automatic lock-on was broken, they could work around it. By predicting exactly how the failed unit would behave, they used subtle timing changes in the commands they sent to essentially force the command into the receiver.
Wow.
It was a total victory of human understanding over a component failure. It saved the entire future of the mission.
Then there was the second major crisis with the scan platform, the thing that aimed the cameras.
The platform got stuck, they figured out it was due to lubrication loss, and they confirmed it by running an identical copy of the actuator in a lab, which failed at almost the exact same number of turns.
And since they couldn't just, overtake Voyager with an oil can,
They had to get creative. They realized they could use thermal stresses. They instructed the spacecraft to alternate between heating and cooling the stuck parts. Different materials expand and contract at different rates, and that thermal cycling created enough tiny stresses to unjam the system.
So all those historic photos of Uranus and Neptune.
We owe them to that clever bit of physics. The book rightly describes Voyager as an intelligent being, part robot, part collective human intelligence at JPL. And the whole thing cost the American public less than a penny a year per person.
An incredible bargain. Let's focus on one of the greatest finds from that mission. Titan, Saturn's largest moon. Why is it considered a window into early Earth?
Titan is unique. It's the only moon in the solar system with a dense, nitrogen-rich atmosphere. It's so cold there that molecules move slowly so the moon's gravity can hold on to it. And that atmosphere is chemically very similar to what we think primordial Earth was like.
And Voyager found some key chemicals in that atmosphere.
Yes, it found simple organic molecules like methane and petroleum, and nitriles like hydrogen cyanide, which is a key ingredient in the first steps toward life. But the most important finding was this complex organic solid called tholin.
Tholin. Why is that so significant?
Because when scientists make this tholin in a lab by recreating Titan's atmosphere and then drop it into water, it produces a whole bunch of amino acids.
The building blocks of proteins.
And also nucleotide bases, the components that make up DNA and RNA, the chemical alphabet of life. Over billions of years, it's estimated that a layer of this stuff between tens of meters and maybe even a kilometer thick has rained down onto Titan's surface.
So Titan is basically covered in the raw ingredients for life.
Waiting for the right conditions. But the surface itself remains a bit of a mystery, a scientific contradiction.
How so?
Early radar suggested global hydrocarbon oceans, probably made of ethane, but orbital mechanics calculations suggested a mix of continents and oceans. The source material suggests scientists were being a bit too Earth chauvinist, assuming it would look like Earth.
So what's the potential resolution?
The idea now is that instead of deep global oceans, Titan might be a world of large circular hydrocarbon lakes, maybe hundreds of miles across, sitting inside impact craters. It's a reminder that we constantly project our own experience onto alien worlds.
We've established the evolutionary imperative and the profound humility. Now we get to the ultimate justification for expansion. Long-term survival. Part 5. A vision of the future. We have to start with the asteroid impact hazard.
We live in a cosmic shooting gallery. Interplanetary violence is routine. Civilization-threatening impacts from objects a few hundred meters across happen roughly once every 200,000 years.
That doesn't sound like a negligible risk.
It's not. The book calculates there's about 1 chance in 2,000 that a newborn baby will experience a collision like that in their lifetime. You'd never get on a plane if the chance of crashing was 1 in 2,000.
And the 1994 Shoemaker-Levy 9 collision with Jupiter was a dramatic, real-time warning.
It was an incredible event. The comet broke into about 20 pieces, and they all just plunged into Jupiter over several days. Even amateur astronomers could see the fireballs. It was a reminder to everyone that the solar system is still a violent place.
We have the technology now to deflect an incoming asteroid, but the book highlights this creates a huge political and ethical danger, the deflection dilemma.
We have all the pieces, telescopes to find them, rockets to reach them, and thermonuclear weapons to nudge them. But once we can do that, we also have the capability to take a harmless asteroid and deliberately send it crashing into Earth.
So it's a terrifying security paradox.
Yeah.
The tech that can save us can also be used to destroy us.
Exactly. If we develop it, it could be misused by a totalitarian state or a madman. If we don't, a natural asteroid might wipe us out anyway. The risk of misuse always comes down to the only a madman argument.
The idea that no rational person would do it.
But history shows us that madmen really exist, and sometimes they achieve the highest levels of political power.
The book uses the chilling example of Hitler in 1945.
Seeing defeat was inevitable, he ordered Germany's own infrastructure destroyed because the surviving Germans had betrayed him. Imagine a leader with that level of spite who has access to asteroid deflection technology. They could create a global catastrophe and blame it on a natural event.
So the only safe policy is an extremely cautious one.
Yes. A combination of accurate orbit prediction, transparent threat assessment, and public education. We need to build in safeguards against misuse and acknowledge that the most dangerous objects in the solar system might not be the asteroids, but us.
This inherent risk brings us back to the core argument for manned exploration to Mars and beyond, even with the immense costs.
The cost is staggering, up to $500 billion. That competes directly with pressing issues here on Earth, so the justification has to be more than just science, which robots can do cheaper and safer.
So what is the true justification?
It's entirely about long-term survival, safeguarding the Earth from impacts and, crucially, hedging our bets against any unknown environmental threat by establishing self-sufficient human communities on multiple worlds.
Putting our eggs in many baskets.
Exactly. Diversifying our portfolio as a species to guarantee the human race continues no matter what happens here.
Which leads to the ultimate engineering goal.
Yeah.
Terraforming. Remaking an alien world to be habitable.
We already alter Earth's environment by accident. Intentional terraforming requires immense power and understanding, and the difficulty varies wildly.
How does Venus compare to Mars?
Venus is way harder. Its atmosphere is crushing, 90 times Earth's pressure, almost all CO2. The proposed solutions are almost science fiction. Gigantic orbital sunshades thousands of kilometers across, or somehow converting kilometers of surface rock into carbonate minerals.
Prohibitively difficult. What about Mars?
Mars is easier. It's a frozen desert with too little greenhouse effect. The goal would be to warm it up, release the frozen CO2 from the polar caps. But even that would likely require destroying unique scientific data, the laminated polar terrain that holds the entire history of Mars's climate.
Which brings up the big ethical question.
The core question is profound. Terraforming requires way more understanding than we have. And the ultimate ethical barrier is our own track record. Can we, who have made such a mess of this world, be trusted with others?
The conclusion being?
The first step in engineering the solar system, the proof of concept, is guaranteeing the long-term habitability of Earth.
Finally, let's touch on our search for a companionship, the search for extraterrestrial intelligence, or SETI.
We're only just beginning. Project Meta, for example, listened to 8.4 million narrow-frequency channels, looking for signals that no known natural process can make, a token of intelligence.
How did they make sure the signals weren't just our own noise?
They had to compensate for the Earth's rotation. A distant radio source would appear to have a steady, predictable drift in frequency. Meta's receivers were constantly adjusted to compensate for that. A real signal would stay locked in one channel, while our own interference would race right through them.
And Meta did find some unexplained candidate signals. What does that suggest?
Well, if those signals are confirmed to be real beacons from other civilizations, we can estimate there could be up to 1 million transmitters in the Milky Way alone.
A substantial number. But if the nearest one is, say, 200 light-years away, we had to deal with a cosmic delay.
Yes, our first strong radio and TV signals went out after World War II. If they're 200 light-years away, their reply won't get here until around the year 2350.
So there's this fascinating possibility.
That we will have become a multi-world species, maybe well-established on Mars, before we get confirmation that we are not alone. We'd have generations to prepare for that historic contact.
So we've taken this immense journey, from our evolutionary blueprint as nomads to the systematic stripping away of our self-importance. We've seen the life-saving lessons from dead worlds and wrestled with the paradoxes of expansion.
The central thread is that our deep-seated nomadic trait is now the long-term insurance policy for our entire species. We had to embrace the great demotions, Copernicus, Darwin, the multiverse, which took away our comfortable illusions and left us with a cosmic view rooted in humility.
But the exploration that fueled that humility also gave us the practical tools to protect ourselves. Venus and Mars informed us about ozone depletion and global warming. A Martian dust storm gave us the nuclear winter hypothesis.
And the ultimate goal is just safety through diversification. Establishing self-sufficient societies on multiple worlds ensures survival. And that diversification won't just be biological. It'll foster new cultural advances, new experiments in social organization.
But our destiny depends not just on technology, but on evolving our social and political institutions just as fast. If we take our violence and short-sightedness to the cosmic stage, we'll have guaranteed our own extinction.
That is the final, powerful call to humility. We have found wonders our ancestors never dreamed of, but so far, beyond Earth, all other worlds are desolate and barren. If our technology keeps growing, our wisdom has to match it. The final mandate is simple. Preserve and cherish the pale blue dot, the only home we've ever known.
Okay, let's unpack this. What truly sticks with you is that after centuries of science and billions spent on exploration, the final conclusion isn't a technical plan for a starship. It's a purely ethical plea for kindness and preservation. The implication is that maybe our entire history as a technological, settled species has just been a brief, only partially successful sedentary experiment, and that true maturity means embracing our cosmic destiny and becoming wanderers once again, but this time with wisdom.